First problem here is to expand x plus 1 to the fifth. So that would be x to the fifth, x to the fourth, x cubed, x squared, x. The 1 is convenient because everything else is going to be 1s. Our binomial coefficients are 1, 5, 10, 10, 5, 1. And then I'll just put a plus sign with them all, put a box around it, and we're all good, right? That's all that one is. This one's a little bit more work because we have to do 2x and negative 3y, so it's going to be a little bit more work over here, but not too bad. 2x to the fourth, 2x cubed, 2x squared, 2x and nothing, and then I'll put the negative 3y to the fourth, the negative 3y cubed, the negative 3y squared, and the negative 3y. So those are coming from the powers that get us up to the 5. 1, 4, 6, 4, 1 are the the binomial coefficients. And so the final answer here is going to be, let's say 2 to the fourth is 16, so we'll get a 16x to the fourth minus 2 cubed is 8. 8 times 4 is 32, and 32 times 3 is 96. 96 x cubed y, negative 3 squared, so that's going to be, let's see, a 2 squared is 4, 3 squared is 9, 36 times 6 is 216. Then here we have a 27 times an 8, so that'd be a 3 cubed times a 2 cubed. Oh, it's 6 cubed again, so that's 216 xy cubed. And then on the end, we just have this 3 to the fourth, and so that's going to be a plus 81 y to the fourth. And so that would be that expansion. Use induction to show this statement. So again, just the inductive step would say that we get to assume that k cubed plus 3k squared plus 2k is divisible by 3, and then jump into k plus 1. So now notice k plus 1 cubed plus 3 times k plus 1 squared plus 2 times k plus 1. We're hoping to show this is divisible by 3. Normally I would try to look for some strategic way to factor out a k plus 1 and see if I can get something cute out of this. But since we're in a lesson on the binomial theorem anyway, I'm just going to expand this with the binomial theorem. So k plus 1 cubed is k cubed plus 3k squared plus 3k plus 1. This would be a k squared plus 2k plus 1, but then tripled. So I'll put a 3k squared and a 6k and a 3, and then that's just a distributive property, which is a 2k plus a 2, right? So notice here, here, and here is k cubed plus 3k squared plus 2k, which I already knew is divisible by 3, thanks to the inductive hypothesis. And then what's left over is 3k squareds, 9k's, and then 1, 4, 5, 6. So what's left over is 3 times k squared plus 3k plus 2, which I could factor further, but I don't really care because look at that. That's definitely divisible by 3. So we have the sum of two numbers which are both divisible by 3, means we have successfully shown the inductive step. And then here we have a 3 equals 12, a 5 equals 2, and we want the nth term of this geometric sequence. So my fifth term, which means it would be my first term times my common ratio to the fourth, needs to be equal to 2. And then my third term, which would be my first term times my common ratio raised to the power of 2, is going to have to be equal to 12, right? Fifth term is 2, third term is 12. So now I will divide these, so that way I end up getting r squared equals 1/6. And so it seems like r is equal to plus or minus 1 over radical 6. So does that allow me a convenient way to go back and get a1? Let's go substitute into here, I guess. 1 over rad 6 squared is 1/6. So a1 times 1/6 equals 12. So a1 would be 72. So my nth term, a sub n, would be equal to the first term, 72, multiplied by the common ratio, which could be either plus or minus 1 over radical 6. So there's actually two different answers to this one. And that would be raised to the power of n minus 1. So when writing this up, I would probably write 1 with the plus, 1 with the minus, as opposed to using this. This is definitely a non-standard notation.